Hi, I'm Craig and welcome to Concrete 101. Today we're going to talk about a raw material that is often confused with concrete. It's a common mistake to talk about a cement truck or a cement sidewalk when what we really mean is a concrete truck or a concrete sidewalk. Cement is actually an ingredient in concrete. At its simplest, concrete is made out of cement, water, and aggregates, or sand and stone. Concrete can also contain other things like additional cementitious materials, pigments, and admixtures. But today we're going to focus on the cement. So what is cement, and why is it so important? Well, cement is a fine powder that when we mix it with water, it reacts chemically and hardens, forming cement paste, or the glue that holds the aggregates together, forming the concrete. And it's important because it affects a lot of the properties of what we make. First and foremost, it has a major impact on the strength and durability of the concrete we make. Proper strength and long-term performance is important to all of the products. Second, the color of the cement has an impact on the final color of our architectural concrete, such as pavers, water-repellent block, and segmental retaining wall units. This is especially important for lighter colored products. And the lighter the color of the cement, the sharper and brighter will be the final color of our pavers and block. Finally, cement has a major impact on the final cost of our products. Cement is the most expensive ingredient in our mix, so if we use just enough cement to get the properties we need but no more, we'll make the most cost-effective products possible. Now, we said that cement affects the strength, and yep, if you use more cement, you get more strength. So for some products that need to be stronger, like pavers, compared to others like concrete block, we'll need to use more cement.
Hey, this is your chef Dean Florentine from the beautiful UP of Michigan, and I'm here to talk about cooking, but cooking with cement. You guys use cement in your products, I use flour in my products. So we're going to talk today about a donut and a bagel, and I'm going to tell you about how they compare to your products. So let's say that I'm going to make a donut. I am going to measure out here and weigh out 1 unit of flour, and I need to add a little bit of water to that and mix it up thoroughly if I'm going to make a good donut, which I would compare to what you make in a concrete block or CMU. Now, let's say that I'm going to make a bagel. I'm going to need twice as much flour, just like you would need twice as much cement in your pavers. So I'm going to weigh out 1 more unit. I'm going to put that in the mixer. And if I put in more flour or more cement, I need to add more water. Now I'm going to make sure that that's thoroughly blended and mixed up properly so that I end up with a good bagel product in the end. So remember, I talked to you a little bit about this donut is kind of like a concrete masonry unit. It doesn't have to be as strong as a paver, and I'm going to show you that right now. As you can see, this donut really doesn't hold up quite as well as it might, but they don't need to be as strong, just like a CMU. Now a bagel we expect to be a little bit tougher. So we add a little bit more flour, just like you add a little bit more cement to your pavers. So we end up with something that stays together. So again, that's just a little bit of cooking and a little bit of cement information from Dean Florentine, and we'll see you again.
So what is cement made out of? Cement is a manufactured material made from a combination of limestone, silica sand, clay, and iron. And how is cement manufactured? Cement plants are built on quarries where the various rocks are mined. The different types of rocks are mixed together in precise proportions and crushed. and then fed into a very long rotary kiln under tremendously high heat of around 2700 degrees Fahrenheit. The high temperature causes the rocks to decompose, with carbon dioxide being released from the limestone and water being released from the clay. The remaining materials chemically combine to form a new material called clinker. This is a dark-colored marble-sized material. The clinker is mixed with gypsum and then ground up to a fine powder that we call cement, which is basically dehydrated rock powder. Different kinds of cement. We talked about cement and water paste being the glue that holds the concrete together, just like flour and water being the glue that holds baked goods together. Besides the amount of flour that Dean uses, he can also use different kinds of flour, bread, cake, gluten-free, to make different kinds of baked goods. Cement is similar. There are basically 4 main types of cement with many different additional classifications depending on how the cement is made or how it performs. To make it even more confusing, there are also different ways to describe them. So all in all, there are more than 20 different classifications of cement. Sure. To simplify things, there are 2 main kinds of cement that most producers use. The first is type 1-2 or general use cement, and the second is type 3 or high early cement that gains strength faster in the first day or 2 compared to type 1. There's also one more type of cement that you may be familiar with, and that's white cement. This is a specialty cement used in architectural products, especially when you want to make bright, light colors. This brings us to the word of the day, which is hydration. And as you guessed it, hydration has to do with water. Specifically, the chemical reaction that occurs between cement and water when they are mixed together. During the hydration process, the dehydrated cement reacts with the water and rehydrates, forming long needles. The needles from the different cement particles grow together and harden into a rock-like substance called cement paste that binds all the aggregate particles together to form concrete. Many factors impact the cement hydration reactions. It's important to understand that hydration is a process with different stages. It has a beginning, a middle, and an end. It's also exothermic, which means that it gives off heat as it reacts, and we can use the amount of heat generated to tell us where we are in the process. Also, the higher the heat generated at any given time, the faster the reactions and the faster the strength gain. Let's look at a typical cement hydration curve at room temperature, and this is a representation of the cement hydration process. You'll notice that there is a heat spike in the first 15 minutes right after the concrete is mixed, followed by a dormancy period in stage 2. For those of you who have steam curing chambers or kilns, the dormancy period is why we don't turn on the heat as soon as the units go into the kiln. If we blast the units with too much heat too early, they will expand and crack because they do not have enough strength to hold together at this point. After the dormancy period, the cement begins reacting again and heating up. This is stage 3, in which the concrete products rapidly gain strength and the cement sets or hardens into a solid piece, usually within 4 hours or so. After that, it enters stage 4 and continues to gain strength in the kiln. When the products are removed from the kiln, they continue to react and gain strength during stage 5. While most concrete products achieve the vast majority of their strength in a few weeks to a month, it's important to understand that the cement hydration reaction keeps on going, even after several years, although the additional strength gain does slow down dramatically. It's also important to understand that cement reactions we just discussed are for concrete made at room temperature. Temperature and curing conditions have a dramatic effect on how fast the cement reactions go and how fast the concrete products gain strength. At low temperatures, the reactions slow down significantly and practically stop when the temperature is below 40 or 50 degrees Fahrenheit. For more on this, let's listen to our local weatherman, Mr. Roger Raincloud.
Hi neighbors, this is Roger Raincloud, your neighborhood weatherman, and listen, your old Uncle Raj had a long night last night, so I'm still wearing party gear, but it'll be okay, we'll get through this. So let's talk about the word of the day, and that word is hydration. We're going to talk about how I can forecast your concrete just like I can forecast the weather. So temperature matters a lot on how your concrete reacts, and that's actually, it matters to old Uncle Raj here because it affects me in ways too. So let's talk about that a little bit. If you look over here and you see the black line, that black line would be concrete that's curing at about 75-degree temperatures. And the first spike happens right away in the first 15 minutes or so, and then it goes into a dormant stage for a couple hours, and that allows you to make it into something. And then you'll see it climbing a hill, and that's gaining more strength when it's in curing. And once it's out of curing, the strength gain starts to slow down just a little bit, but it'll continue for quite a while. Now, they gave Uncle Raj here a little clicker, so we're going to try this out. Damn clicker. So anyway, let's say that you live in the Southwest, say down here in Phoenix. Down here in Phoenix. There we go. So if you're living down there, I want you to compare that to the red line over here on the chart, and you're going to see that it gains a lot more strength earlier, and as it comes down, it's going to start gaining strength after the dormant period a lot faster. And that'll continue as long as that warmth is there. So the warmer the temperature, the quicker the strength gain. Now let's just say that you live over here in the northeast part of North America, let's say in the GTA. That means the Greater Toronto Area for you non-Canadians. So if you're up there this time of year, it's pretty cold. So we're going to look at the blue line. Now the blue line would tell me that you don't have a lot of heat. It might be cold, might be just above freezing outside, and maybe your curing isn't really good, so it doesn't gain a lot of heat, and heat in concrete makes strength. So again, the warmer the temperature, the quicker the strength gain. The colder the temperature, the slower the strength gain. This is your old Uncle Raj saying, have a sunny day.
So let's review what we've learned about cement. Cement is made by combining specific amounts of different rocks and heating them to a very high temperature in a kiln. During this process, water and carbon dioxide are driven off, and we form new compounds called clinker. When we grind this to a very fine powder, we get cement. When we make concrete, we add water back into the cement and mix it with aggregates. This does two things. First, it makes the concrete workable and formable. And second, when the concrete products are put in the curing chamber, the cement and water react during the cement hydration process and stiffen and set, becoming solid again. This is the magic of cement. It starts out as dehydrated rock, becomes formable when we add water, and then returns to rock during cement hydration. When combined with aggregates, this allows us to make the solid, durable products we sell today. Besides allowing us to make concrete, cement also has a major impact on the strength, durability, color, and cost of our products. And because it's expensive, we only use as much cement as necessary, but no more than we need. So that's the basics of cement.
So that's all for today, folks, but feel free to check back with us anytime on our website, acmchem.com, where you can get more information and more videos on Concrete 101.